Hello, today I'm going to show you how to implement a simple collision detection and environment mapping using a LIDAR device connected to Jetson Nano main unit of my robot. LIDAR is it stands for a light detection and ranging, so in general it's kind of simple device which is generating a laser signal around, and it is measuring the reflected light that is hitting the receiver, and thanks to it it is able to calculate the distance for each angle around the head, yeah, and all those calculations in form of scan are sent through the USB interface to the main unit, which is doing a kind of decision making, also visualization and so on. So it is pretty simple device. However, I'm using the very simple model, which is generating like 2D two-dimensional data. There are 3D very fast LiDARs that are used for autonomous vehicles, but in my case it's enough to have just two-dimensional environment mapping, because I'm especially interested what is in front of my robot. So while it is free walking, I need to detect some obstacles in front, so then my robot will have to change the direction of movement. Now you can see this is the new interface of my Python Flask application that is communicating with the robot. This application allows to trigger some free walk, also manual control. I did some adjustments to my robot which I will discuss maybe in different movie. Now let's focus on LIDAR. So as you can see here, we have the LIDAR scan button, which I will use to show you environment mapping functionality. So as you can see, the LIDAR started to spin, and now it is scanning environment around in my room. If I show you the polar chart that this application is creating, so you can see that the mapping area is constantly changing. So here we have everything what is in front of my robot, which is close to 0 degree. So now if I, for example, put something in front, which will be my hand, now you can see that this chart changed. So there is probably some obstacle in front, right? If I move out my hand again, you can see that there is no obstacle in front of my robot, like in 3 meters ahead. Okay, now I will stop this LIDAR and show you how I implemented the behavior of this LIDAR in controlling it using Python library and plotly.js front-end JavaScript library. Okay, let's switch to the code. Let's start from the front end. As you can see, in order to visualize data coming from RPLidar, you need some chart library. In my case, it is plotly.js, but you can use this.js as well. They are also offering a wide variety of charts. In my case, I am especially interested in polar chart when I have angles around, actually degrees, and the LIDAR is located in the center, and here I have a distance. Yeah, so thanks to it, I can easily, in this scattered polar chart, draw a line representing obstacles or walls or anything around the LIDAR. Also, for communicating with LIDAR, you need some Python library. I did use the RPLidar library from Slamtec. This is very lightweight library. There are some errors. I found that there are some byte inconsistency errors sometimes, but I found a workaround for this, which I show you in a minute. So you need to install this library. Okay, let's start from the where the action is actually triggered. So if I click the start scan function here, actually LIDAR scan button, it will call start scan function created in JavaScript on a page, which is establishing a WebSocket connection with the Python server Flask application and setting some handlers. The most important one is the LIDAR scan ready handler, which is invoked every time the data is pushed from the server to the front-end client, so it can then hand over the LIDAR samples to the plotly.lidar data function here. So this plotly.lidar data function is using the plotly.js library with the scatter polar chart. And in reality, the LIDAR samples is the data structure where the key is the angle and value is the distance for that particular angle. So you can draw automatically the line with the use of the plotly.js library here. Of course, you can manipulate with colors, fonts, and so on, also with the size of the chart, but it's not important for now. Okay, if we switch to the server side, to the Python side, here I have the environment mapping service class, which is using this RPLidar library from Slamtec Robotics. And in a constructor, it just connects using some port to the RPLidar. Once it is connected, it is ready to serve RPLidar data. But the key point are the start collision detection function and also start scanning function, which are launching separate threads that are intended to collect RPLidar data. So start scanning launches a thread where the argument is a scan function. If I scroll down to the scan function, it is just monitoring the event here, stop LIDAR thread. If it's not set, it's scanning data. It's calling collect scan data. If something wrong happened, as I mentioned earlier, so we might sometimes get a RPLidar exception, then I am disconnecting and connecting again to the LIDAR. So the situation is fixing itself with the use of such two calls. I didn't found any better workaround for this. And the collect scan data itself method, it is collecting a data as just invoking the piece of code which is on the library side. It's enumerating over scans, and I am taking each scans, which is in reality a tuple consisting from the degree, distance, and signal quality, and I'm ignoring signal quality and creating a kind of dictionary which I called angle to distance dictionary, where the key is the angle and the value is the distance. And such a structure I am handing over to LIDAR scan ready callback. And this callback is invoked here in the main application class. And what it does, it's just simply sending as a JSON the angle to this structure over the WebSocket connection. and the front end is consuming this and is able to draw a chart. Now, if I switch back for a second to environment mapping service, as you can see, we have the collect scan data method, which is actually used by scan method, which in turn is used in two cases. One is just for scanning and one is the collision detection. So this is the real function that is used by my robot. It is doing exactly the same thing, although the callback function doesn't push anything to the WebSocket because it's only for visualizing purposes. I am calling the collision evaluation callback, where I'm just checking the most interesting angles in front of my robot. And if any of this angle is close to some obstacle, I am setting collision event, which is monitored by the service, quadruped robot service, which I show you in a second. So this service, give me a second. Okay, it's here. So yeah. So we have the free walk with collision avoidance method, which is triggering a threat that is controlling robot movement. And also it is triggering a threat through this environment mapping service, which is triggering a scanning, yeah? And the collision event is handed over to that threat. And every time this event is set, the change of the direction is executed here in worker treat function. So if we are waiting for the collision event, if it happens, then we are just turning on front light, which is an indicator of an obstacle, and then we are trying to turn right. This is just a prototype. We can arbitrarily call turn right or turn left, and we are keep turning right till the event is not set. Okay, so I will show you the robot in action in different movie, but for now I just wanted to focus on the code. The code is very simple. I believe I could use potentially the ROS framework to implement this, but the learning curve of ROS framework is not very convenient for me for now, so I just stick with this very simple library. Okay, thank you for now.